kind of rushed through at the end of the last class, deciding whether or not a reaction occurs. So with the single replacements, the first thing that you have to do or you're responsible for is predicting products. Okay, so if we pick this silver one here, I'm predicting that silver would combine with the chloride. Okay, I am predicting then that the aluminum would be by itself. Okay, that is the definition of our single replacement. I have to ensure that the products I've predicted are stable, okay, or balanced. So I would have to evaluate the charge. The charge on silver in a compound is a plus 1. The charge on chloride is minus 1. Is that formula correct? Yes. Why did the 3 not move across? It says silver or aluminum chloride with 3 there, right? Why is the 3 not over here?
Because then it would have been balanced.
Okay. It's actually an unfortunate question. Okay, to get at the root of that question, it's, well, why is there a 3 here? The 3 is so that chloride balances aluminum. Is chloride with aluminum? No. So the 3 shouldn't be there because not with aluminum. Okay? We have to understand why we use those subscripts. Okay? Sometimes the subscript is there as a balancing. Sometimes the subscript, in the case of nitrate, is part of the name. There are 3 oxygens in nitrate. If I remove that 3, it's no longer nitrate. So the 3 is part of what makes that nitrate. The 3 here is not what makes it chloride. Okay, that is a challenging concept because the numbers are showing up in the exact same location. Same number, same location, different meanings. Okay, so you have to understand why we're placing those things in there. Kind of, sort of? Okay. So first step, single replacement, we predict. Okay, and we would go through and say what was the double or the single replacement reaction. So we've got it drawn. Okay. This is a potential plan. To decide if this plan came to fruition, I have to use the activity series. So I would go to the activity series and I would find the 2 things that I'm concerned about. Aluminum and silver. Okay. Aluminum is higher in the activity series. That means it is more likely to be coupled, meaning aluminum wants to be with something else. With that information, I can go back to my reaction and find aluminum. Where is aluminum coupled to something else? Right here. Okay. I could also look at silver. Silver's lower in activity. Okay. Because it is lower in activity, it does not want to be coupled, meaning silver wants to be by itself. So I go back to my plan and say, where is silver by itself? On the reactant side. When I go through to now run the plan of this reaction, what am I going to mix? All reactions, what do you start with? All reactions, what do you start with? Every single one of them. Okay. One suggestion was a product. Remember, reactions are a plan. Okay. So your plan in this class is to get an A in the class. That is your plan. You walk in the front door, poof, you have an A. Is that how it worked? No, we don't get the goal at the beginning. What do we get? All the work we've got to put into it. Okay, the goal comes at the end. What do we start with? Chemistry, what do we start with in a chemical reaction? As a hint, we call reactants. Where are the reactants in my chemical equation? The left-hand side of the arrow. Okay, so if I'm going to run this plan, I mix these 2 species, and if the reaction occurs, I would get those products. That's what a chemical reaction means. Okay? If I layer now in the information from the activity series, The activity series says that silver wants to be by itself. So when I mix silver with aluminum chloride, what happens? Nothing happens. No reaction occurs. Does that mean the plan is invalid? No, the plan is still valid. It's still a true plan, but it just didn't happen. Okay? So we have to evaluate our single replacements both by doing what is the plan, what products could we get, and then we have to decide, did we get them? So two harder questions get layered into your single replacement reactions. It requires looking at an activity series. How many of you want to memorize the activity series? All right, well, let's try that question again. How many of you do not want to memorize the activity series? Okay, there we go, just checking. Okay, the microphone was on. I agree, I think that's an awful idea. I don't want to make you memorize the activity series. So on an exam, I will give you a condensed activity series. Okay, that will be put on the very first page of the exam. Take a look at exam 1, guess what you see in page exam 1. You see an activity series. I don't give you the entire activity series, I just give you mostly the things you would need and a few extra ones just because. Okay, so you're responsible for going back to the front of the exam to pull that information off. Make sense? Okay. Some materials, some metals are so reactive that they will actually react with water. Okay? Water doesn't have a metal to exchange, but it does have a positive hydrogen on it. That hydrogen is not very positive, but if the metal is reactive enough, it can also do a single replacement reaction. Okay? These would be known as active metals. Really, the better way of saying it is superactive metals. Right? So these reactions can and do happen. I don't expect you to memorize them. I don't even really expect you to do much with them other than say, well, those are valid single replacement reactions. That's it. Okay? So I just want you to be aware of that. So if you've ever seen videos where people take sodium or lithium and throw them into a lake, that's what's happening. Why does the thing come launching out of the lake? There's lots of things that super react that don't go launching places.
Gas is produced.
What do we produce? Hydrogen, gas. Okay? If I take a brick and I throw it in, it's going to contact water where first? On the bottom. And what's it going to produce? Gas. Where? On the bottom. What is that gas now going to do? Try to get out. But the solid's blocking it. So what does it do? It pushes the solid up out of the solution. That's why we get the brick launching in and out of the lake. Okay? It's because of that hydrogen gas. Okay? And if we're extra lucky, it produces enough heat that the hydrogen gas ignites and we get a little fireball with it. Okay? So this transitions us into the oxidation and reduction chapter, okay, which you watched a video on. You've also read at least 2 sections in the textbook and hopefully just 2 sections. Oxidation and reduction are really referencing electrons on an atom, okay, and ultimately the balance of protons and electrons on a single atom. We've seen the balance of protons and electrons before. Okay? We saw that when we looked at charges and how we put together compounds, okay, to come up with nomenclature and names and formulas. Okay? Charge is really just the broader term for oxidation and reduction. Okay? What these are getting to is this concept of oxidation state, okay, versus charge. The oxidation state applies to a single atom. It's the balance of protons and electrons on a single atom. Okay? The charge applies to a unit. Well, if my unit is a single atom, then the charge and the oxidation state are the same thing. If my unit is a larger molecule, then I can't reference the charge and oxidation state because the molecule doesn't have an oxidation state. Only atoms within that molecule have oxidation states. Okay? When it comes to oxidation state, we have to know certain rules to help us move through it. Rule 1, we need to know our ionic compounds. Okay? Because if I have an ionic compound, I can split the ionic compound into the ions. So instead of looking at a formula for calcium hydroxide and not being able to figure out oxidation states, I can split calcium hydroxide into calcium ion and hydroxide ion and then determine oxidation states. So it can simplify my solving process if I acknowledge ionic compounds. Okay? The next big one is oxygen is always a -2. Okay? Well, oxidation state is the balance of electrons and protons. Why would oxygen always take 2 electrons from whatever it was connected to? Well, nitrogen needs to take 3, but if I put nitrogen next to oxygen, oxygen's a -2, nitrogen is not. Why would oxygen take the electrons from nitrogen? It's not just to fill its octet. Oxygen is more electronegative than nitrogen, meaning oxygen will steal those electrons from the nitrogen, changing nitrogen's oxidation state. Why would oxygen always steal 2 electrons? Because it's more electronegative. It's the second most electronegative element on the periodic table. It's always going to take 2 electrons. Is there an exception to that? Fluorine is more electronegative than oxygen. So if I bond fluorine to oxygen, is oxygen a -2? No, because fluorine's more electronegative. There's another exception. Well, fluorine's more electronegative than it. Oxygen's the second most. Everything else with oxygen is less electronegative than oxygen. How could there be another exception?
Hydrogen, right?
Not hydrogen, not helium, not lithium, beryllium, boron, carbon, nitrogen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium, scandium, titanium, vanadium, chromium, manganese. Not mercury either. Oxygen. I know, Mike, you said about oxygen. Yeah. What happens when oxygen's bonded to oxygen? Which one's more electronegative? They're equal, which means can they steal each other's electrons? No, the oxidation state changes. Okay? Because we don't have that difference in electronegativity. Okay? The next big deal that we have to worry about is the sum of the oxidation numbers. Okay? If I add up the oxidation numbers for every single element in an individual unit, okay, that's now looking at the balance of protons and neutrons for every single element in a compound. If I add all of those up, what does that then have to equal?
The mass of the
That's going to be now the balance of protons and electrons in the compound. What is the balance of protons and electrons in a compound? The overall charge. Right? So we get this formula that comes out of it, which should look really familiar because we had effectively that same formula when we went through to solve nomenclature. And when we did nomenclature, I said, you need to learn this formula because we're going to use it again. Okay? And if you just do nomenclature with the crossover, you've lost this understanding, which then means you now have to learn it again. Okay? Try to give you a hint so that you could do better further on down the road. Okay? We have to then apply those rules to a reaction. And I would determine the oxidation state for every single element within the reaction. Once I've done it to every single element, I can then compare what happened to that element in the course of the reaction. So let's take a quick look at the example here. What is the oxidation state in this first unit? Okay. How is it 0?
It's the same as the charge.
Okay. There is one calcium atom times an unknown oxidation state. There's no other elements, so 1 times x equals. What does it equal according to the formula?
0.
According to the formula, I want words.
Oh, charge.
Charge. Where's the charge for this formula? This is the fun part. The charge is always given to you. Nope. Calcium as an ion is a +2. This isn't calcium ion. This is just calcium metal. Where's the charge specified?
It's not, but it's
The same place it's always specified. The upper right-hand corner. Is there anything in the upper right-hand corner? No, which means its charge is 0. So what is the oxidation state? Well, now I can solve for x. X equals 0. What happens when I move over to the other side of the equation? Let's look at calcium again. I want to determine the oxidation state for calcium here. This formula becomes a little bit more challenging. How many calciums are there? 1 times its oxidation state. Its oxidation state is determined by its charge, but I don't know the charge on calcium because all I've got is this big compound. So it's an unknown variable, x, plus the next element. What's the next element? Hydroxide is not an element. That's a good name for that complex ion, but that's not the next element. What's the next element? Oxygen. How many oxygens are there? 2 times its oxidation state plus, what's the next element? Hydrogen. Okay, how many hydrogens? 2 times its oxidation state. Again, I got to solve for it. This now equals what? English, the overall charge, which in this case is 0. Okay? There are an infinite number of solutions to this. Right? Even if I go through and say, well, you were told to memorize that oxygen is a -2, we could simplify that. We could put in a -2 there. I still have 2 variables. I wouldn't be able to solve the equation. What is the very first rule?
Know the charges for ionic compounds.
Know your ionic compounds. Is this an ionic compound?
Yes.
How do I know it's an ionic compound?
It's a metal or non-metal.
Metal and a nonmetal. Because it's an ionic, that compound I can split. So instead of solving that big long equation with an infinite number of possibilities, I can split this into the 2 pieces. What are the 2 pieces?
Calcium hydroxide.
Calcium ion, which is a +2. How do I know it's a +2? Second columns are all +2s. What's the other piece? Hydroxide with what charge? Minus. Do I need to worry about that too?
Yes.
No. Why is that 2 there? Not quite. Why does that 2 there? Balance what? To balance hydroxide with the calcium. What did I just do? I split them, so they aren't with each other anymore. Do I need the 2 anymore? No, because hydroxide's not with calcium anymore. Okay? So I can simplify my system. Now when I go through and solve, well, calcium, how many are there in that formula? 1. I don't know its oxidation state. This has to equal the overall charge, which is +2, but you can get away with 2. X equals +2. What happened to the calcium in the course of this reaction? I went from a 0 to a +2. How do I go from a 0 to a +2? Okay, so we'll hear a couple terms float out there. We immediately started hearing reduced, okay, or oxidized. I would argue you shouldn't be using those terms yet. We should look at the basics of what happened. Oxidation state is dependent on the balance of protons and electrons. Do I have to worry about the protons changing here? Why not? How do I know the number of protons isn't changing? Yes. It's what defines the element. Did the element change? No, so the protons didn't change. What did change? The electrons. How did the electrons change? Okay. It lost electrons. Okay, but I became more positive. If I lose something, do I actually become more positive?
Sometimes.
If I lose debt, I'm going to become pretty positive. I'm going to be happy about that. That's a good thing. Okay? Debt is a negative thing. What are electrons? Negative. So when I lose a negative, I become positive. Okay? Now I have to add in that extra layer to it that Cody was trying to drop in. I don't want to go through and constantly reference things by loss of electrons. Why not? Well, the original terms for what these reactions are oxidation and reduction, happened before we knew we had electrons and protons. Okay? So those definitions of oxidation and reduction now have to get layered over top of what's happening here. Okay? Loss of electrons is oxidation. Okay? I know the calcium was oxidized in the course of this reaction. Okay? Where is that term oxidation coming from? Oxidation sounds kind of like oxygen, from the root ox or oxy. Okay? What happened to the calcium in the course of this reaction? How many bonds to oxygen does calcium have here? Zero. In the product? Ooh, we've increased bonds to oxygen, hence oxidation. Okay? What happened if we went through and take a look at hydrogen? So the other species, instead of calcium, let's look at the water molecule here. What happened? If we look at hydrogen, it had a bond to oxygen, right? Look at hydrogen in the product. No bonds to oxygen. What happened to the number of bonds to oxygen?
Reduced.
They were reduced. Oxidation and reduction centered on the presence of oxygen. Why oxygen? Oxygen is the most reactive species in the world. That might be a bit overstated, but that we're exposed to. Okay? So oxygen was a readily available reagent, so we defined our terms based off of how they interacted with oxygen. We found plenty of other reactions that don't involve oxygen that are still transferring electrons. So we have to expand our definition from just looking at the oxygens to now also looking at the change of electrons. That's our loss of electrons and gain of electrons. Okay? So we can define the loss of electrons as oxidation, and we can define the gain of electrons as reduction. Okay? Leo says Gur. Leo, we go into our Greek, Latin, Italian astrological signs, is
Lion.
a lion. What do lions do?
Faker.
They gur. Okay? You may have also heard oil rig. That's a horrible one. That's not very nice. Leo says gur is cooler. Loss of electrons, oxidation. Oil rig, oxidation is loss. Well, I lost my keys, so I'm oxidized? What did I lose? I don't know. All it says is oil. Oxidation is loss. I have no idea what I've lost. That's why that one's dumb. This one says in it, literally, what did I lose? Electrons. Oxidation. That's why this one's better than the stupid oil rig thing that everybody populates. From what I understand, the biology department pushes oil rig a lot, which I find very weird. Biology is all about what? Living things. You mean like lions? Yeah. Okay. What is biology not about? Dead things. You mean like petroleum? Like oil, and yet you're using oil rig as your mnemonic device. Come on, biologists, you can do better than that. Leo says gur. Okay. The next layer that makes this extra fun is we can reference something known as the agent. Okay. If you're familiar with the comic Spy vs. Spy, okay, if you were a spy in another country, okay, you're trying to find out information, say, about Russia. Why not? They're in the news. Okay? You're going to be acting like a Russian. But what are you doing as a spy? What does that mean? You're collecting information about Russia, and then what are you doing with it? You're taking it back to somebody else. Our oxidizing agents and our reducing agents are very much the same thing. An oxidizing agent goes into the other world and says, you're oxidized. Okay? I am causing you to be oxidized. Well, if you are oxidized, what happened to you? Leo says gur. You lost electrons. Well, if you lost electrons, something had to gain those electrons. If I'm the one making you be oxidized, who gained the electrons? Me. What happened to me? I was reduced. So I am an oxidizing agent, and thereby I was reduced. Okay? They're the opposites of each other. So you have to be very careful when you see reference to oxidizing agents and reducing agents, because they can get confusing very, very quickly because they're opposites. So the ing agent should be a red flag that you've got to slow down. The other word that needs to pop up is if you see ant. So you can say oxidized or oxidize, but if you make it ing, it's doing the opposite. If you make it oxidant, it's the opposite. If you make it reductant, it's the opposite. Okay? Just be aware of those terms. Okay? So let's just take a look at the first one. Okay? I will give you 3 minutes to determine the oxidation states. If you do it faster than that. So for those of you still working, the oxidation states are specified. Somebody noted a pretty quick observation on this. When we go through to solve oxidation states, how do we do it? The number of the element, how many are in that first one? 1 times the oxidation state. I don't know what it is. There's no other elements, so that has to equal the overall charge. What's the overall charge for that? A plus 2. Solve for x. Plus 2. What's the oxidation state for tin plus 2? Plus 2. Yeah, the charge and the oxidation state ended up being the same thing. Okay, it doesn't have to be, but it could be. Okay, so now the next layer. Okay, what happened to tin in the course of that reaction? Okay, we went from a plus 2 to a plus 4, which means I lost electrons. If I've lost electrons, I was oxidized because of good old Leo. Okay, if I was oxidized, what did I cause to happen to the other one? A reduction, which means I was a reductant. What happened to the iron plus 3? We could go with reduced. Okay, that's probably the easier one to see there, because gained electron is what actually happened, and I completely agree with that, but why would it be easier to look at the oxidation numbers to say it was reduced? What happens to the numbers? You go from plus 3 to plus 2. It gets lower. You mean it was reduced? Oh, yeah, there it is. Okay, officially, yes, better answer. It had to gain electrons. Okay? It gained electrons, and that's why we went from a plus 3 to a plus 2, because I gained debt. I'm losing money. Okay? If I was reduced, what did I cause the other thing to do? Be oxidized, so I could reference this as the oxidizing agent. Okay? So, what questions could be asked for this? Identify the oxidizing agent. All right, we just worked it all out, so the oxidizing agent would be no. Because this is not the oxidizing agent. Iron plus 3 is the oxidizing agent. So we have to be a little bit more particular in our answers to make sure it's clear which one we're referencing. Okay? Typically, though, let's take a look and see if, yeah. So let's look at the next one. And we'll look really quickly at this one. So identify the reducing agent. What do you have to do to solve this? What are you suggesting? I want to know which species is the reducing agent.
Nitrate,
How?
because it is causing copper to oxidize.
Okay, so we're running into problems with all the terms. So I would argue as soon as you see reducing agent, you should change the question. I don't want to identify the reducing agent. I want to identify
What oxidized?
what was oxidized. How do I know it was oxidized?
Loss of electrons.
Loss of electrons. So now I can go through and look at this equation and try and come up with, as quick as possible, the species that lost electrons. Okay, I could go through and do this and identify the oxidation state for every single element. I don't have to. What I will go through and do is identify the easiest ones. What would be the easiest one to identify? Copper. Copper in the reactant is all by itself. What's the oxidation state? 0. Copper in the product, all by itself. What's its oxidation state? +2. To go from a 0 to a +2, what happened? I lost electrons. What was I looking for my answer? The species that lost electrons, because it was oxidized, which thereby means it was the reducing agent. My answer is, holy crap, I got the answer without having to do all of the oxidation states. What if I found out or asked for the oxidizing agent? Well, I found the one that was oxidized. If I want the oxidizing agent, I want the one that was reduced. It has to be the other one. I don't have to solve them all. I just have to solve one that's easy. The other one must be it. Right? This doesn't work always because sometimes you have equations that are a little bit more complex. We start with 2 things and we ended with 3 things. Okay? So we can't just say, oh, it's the other one. Okay? So it's not a perfect system, but it works for probably 99% of the questions you'll see in this class. Okay? So if you want answers to those, they are on the slides. All you'd have to do is print out the slides and all the answers are there. Okay, so you can see that information and get it. Okay? The next part is balancing redox reactions. Okay? Can we balance this equation?
Yes.
Yes. Is it balanced? No. How do we balance it?
Zinc in the middle.
Zinc in the middle. On the left, how many do I have? 1 on the right? 1. There's nothing in front. I'm not looking at its charge. I'm just looking at how many are there. Hydrogen. How many on the left? On the right? 2. Hydrogen's not balanced. How do I fix it? Good? Okay. Now we start over. We do it again. What do we find? It's now balanced. So cool, it's balanced. Not a big deal. Why is Mike pointing out that we have to worry about balancing redox reactions? Because that was really straightforward. Look at the next one. How many tins?
2 on the right, left side.
1 and 1. How many irons? 1 and 1. Is it balanced? Yeah, it sure looks like it. Okay. We also have to balance charge. Why do we have to balance charge? Well, what is charge? Electrons. Electrons determine charge. Electrons are matter. So just like our elements, we can't create or destroy matter. We have to make sure that our electrons also balance. We can see our electrons by looking at the charge. What is the charge on the left-hand side of the equation? Plus what? 5. Plus 5. We have tin, which is a +2. Iron is a +3. If I add those 2 charges together, I get +5. What is the charge on the right-hand side? +6. Is the charge balanced? No. So we need to balance it. Since we said charge was electrons, we just have to add an electron to our equation. Where would we place the electron? The left-hand side, good idea. Let's go ahead and throw that in there. What is the charge on the left-hand side of the equation now? +3, +2, -1. 4. Did our equation get closer or further from being balanced? We added it to the wrong side. That's okay. We screwed up. We fix it.
How can you just add an electron?
We'll deal with that in a second. Okay, so I placed the electron on the wrong side, which means I need to place it on the other side plus an electron. Now what would the charge become on the right? +5. Now my charge is balanced, so now my equation is balanced. This says when I run this reaction, I produce an electron. The electron just doo-doo comes into existence, and there it is. Okay, so what this statement is saying is that electrons can exist on their own. Is that true? No, it is not. Okay, We know this to be true because when you walk around through the air, you don't get electrocuted. Okay? So electrons cannot just exist on their own. That electron has to go somewhere. This equation is not appropriately balanced, even with that extra electron, because the electron cannot come into existence. Okay? Something must pick it up. Okay? Our equation is not balanced. We don't have a proper rule set to figure this out. That's why we invent a new system. We look at half reactions. So I will look at half of the reaction at any given instant. Because I'm only looking at half of the reaction, I now can use electrons. Why not? Or why now can I use electrons to balance a half reaction? Because it's only half running. I can't have a reaction run at just half time. Okay, so by only looking at half, I have to make sure that it balances with the other half. Okay, so which half do I look at? Can I balance iron with tin? Why not? Well, they're not the same element. I can't balance iron with tin because they're different elements. So that's a horrible half of the reaction to look at. What should I balance the iron with? Iron. Okay? Does the iron balance on both sides? How many irons on the left? 1. How many irons on the right? Does the iron balance? Yes. Does the charge balance? No. Okay. The charge doesn't even out. I have to make sure the charge balances out. To do that, I will add electrons. I'm now allowed to add electrons because I'm not looking at a balanced full equation. I'm only looking at half of it, so I'm allowed to use electrons. Where should I place an electron? If I place 1 electron on the left, what's the charge on the left? +2. What's the charge on the right? +2. And our equation is now balanced. Cool. I'm going to do the same thing now, but with the other half of the reaction. What's the other half of the reaction? Tin +2 going to tin +4. Is the tin balanced? Yes. Is the charge balanced? No. +2 and +4 don't equal each other. How do I balance the charge? I need 2 electrons on the right-hand side. If I added these 2 equations together, okay, I would notice electrons show up on both sides of the equations. I could condense them by subtracting 1 to the other side. I would have a leftover electron. We would have the equation that we just went through and said was an invalid equation. So when I add these 2 up, those electrons must equal each other. Okay? I need to make sure that the 2 electrons produced by tin are consumed by iron. But iron only needs 1 electron. How can I make that be 2 electrons? How do I make 1 a 2? Multiply it by 2. If 2 electrons go in, how many irons do I need? I would need 2 iron plus 3s. How many irons would I need to produce? 2. So I'm multiplying by coefficients to get them to balance out. If we now add all this stuff up, I get 2 electrons plus 2 iron plus 3s plus 1 tin plus 2 goes to 2 iron plus 2s plus tin plus 4 plus 2 electrons. The electrons show up the same on both sides of the equation, so what can I do? I can subtract 2 electrons from both sides of the equation. I'm just going to cross those out because they now disappear, okay, because they're canceled with each other. Now let's look at the equation. How many irons do I have on the left? On the right?
2.
Tins on the left. Tins on the right. Ooh. Just like we had before, it's balanced. The element's balanced. What about the charge? Because the charge was the challenging one. That's what failed last time.
Still at 5 and 6.
There's still 5 and 6. Does anybody want to challenge that statement? How many irons are there? There are 2 iron plus 3s, which means iron is contributing plus 6. Plus the 2 from tin gets me a +8 charge. What's the charge on the right-hand side? Well, there's 2 iron plus 2s, which means that is a +4 plus the tin. What's the charge? Does the charge balance? There it is. Okay? So the half reactions allow me to see the electrons and effectively use them as kind of a, I wish I knew the mathematical term for it, but a way to kind of check my work or balance it out. Okay? It's like carrying ones. If you did addition, right? 9 plus 9, well, that's 18, so that's 8. I can carry the 1. The electrons, in this case, allow me to show that so I can see that work so that I can balance this system out. Kind of, sort of? I'm going to take that as a yes. Okay. We get now about 4 or 5 slides going through stepwise each of those processes because for whatever reason I decided I wanted it typed instead of handwritten. Okay. So when we go through and look at balancing, we have to come up with other ways. I'm going to tell you the bottom one you should just leave alone. Ignore that. Okay. The top one we looked at, we didn't need to balance charge because we did it with atoms. When we did it with atoms, did it actually balance the charge? What's the charge on the left-hand side? +2. What's the charge on the right-hand side? +2. Actually, it did balance. Okay? We didn't even have to think about charge, and yet that was a redox reaction. Okay? The presence of the other elements, the counter ions, helped us to balance that. Okay? But there are other cases where we don't show those other elements or those other counter ions. In those cases, we tend to need to come up with another way to balance. That's the half reaction method. Okay? So when we balance equations, we start with our standard method. If we suspect that we have to deal with charge, we'll look at the charge and we may have to split that into the half reactions. It is much more advanced, it is much more difficult, which is also why it plays a smaller, more limited role on your exam. Okay? So here's balancing question. Okay? The question is how many electrons were transferred in the course of this? Okay? What becomes the problem with this question? Number 1, it's not balanced. Number 2, how many electrons do you see in that equation? Remember, the symbol for an electron is E-. Oh, they're not written there. How would we possibly know? Well, maybe when they were balanced, we'd see the electrons. Do electrons ever show up in a balanced equation? No. When did we see the electrons? In the half reactions. So we would have to go through and split this equation up into the half reactions to see how many electrons were balanced or transferred in this. This one becomes a more difficult question. Why does it become a more difficult question? In the previous case, we tried to make 2 electrons equal to 1, or rather 1 electron equal to 2. How did we do that? Multiplied by 2. Can I make 2 electrons equal to 3? Can I make 3 electrons equal to 2? No. So I can't just look at one equation. I have to look at both equations. What is the lowest common multiple between 2 and 3? 6. How do I make the 3 a 6? Multiply by 2. 2, 2, 6. How do I make the 2 a 6? Multiply by 3. 6, 3, 3. Now when I add the 2 equations together, I will get a final balanced equation. 3 copper plus 2 plus 2 aluminum. What's the charge on the left-hand side right now? Okay. There's 3 coppers. Each of them are a plus 2. We get a plus 6. Charge on the right-hand side. There's 2 aluminums, each of them at a plus 3, plus 6. Our charge is balanced. The element's balanced. There's our balanced equation. How many electrons were transferred in the course of that reaction? Okay. Just to give you an idea of possible multiple choice, A, 2, B, 3, C, 6, D, 12, and E, 43. What should you immediately do? 43, that didn't make any sense. Okay. Where did the 2 come from? Balancing the copper equation. Where did the 3 come from? Balancing the aluminum equation. Both of those are numbers that came up in solving this, but not solving it correctly. Where does the 6 come from? The number of electrons, right? Once we balance that out. It's also our charge. Okay. That's an interesting observation that I'm not sure I trust, by the way. Where did 12 come from? Because if I add 6 to 6, I get 12. One of the most common wrong answers for this kind of equation is D. Okay. Well, there's 6 on each side, so together that must be 12 electrons. They're on opposite sides of the equation. They cancel each other out. There's only 6 electrons. Aluminum gave up 6 electrons. Where did those 6 electrons go? Directly into the copper. The blue 6 and the purple 6 are identical electrons. Only 6 electrons are transferred in this reaction. Okay? Fun stuff. That is our single replacement kind of summary. This ties back to single replacement because if we look at the reaction above, that is technically a single replacement reaction, though it is kind of buried in the chemistry because we're showing ions as opposed to showing the compound that they go with. Okay? So it's a harder one to identify. I wouldn't ask you to identify that one as a single replacement. Okay? Which gets us to converting as a process. Okay? Everybody fights with this process in this unit. Okay? Everybody. From the best student to the worst student. Because they think it's a waste of time to deal with this process. It is a waste of time to deal with this process when you already have an algorithm to solve it. Okay? The only reason we're making you do this process is so that you trust the process, because in the next unit, you no longer have an algorithm. If you don't have an algorithm to solve it, you're dead in the water because now you don't have a process also. Okay? So when you go through and do any of the conversions, follow the process. Step 1, what are you trying to obtain? What is your goal? Step 2, what were you given? Step 3 is really compare step 1 to step 2. Are they the same thing? Right? If they are the same thing, what happens?
That's the unit.
You're done. You solve the answer. It's done. That's it. Okay? If they aren't the same thing, because that would be a dumb question, okay, you're now going to have to come up with some conversion factor. Okay? Identifying that conversion factor right now is just looking it up. In the next unit, you will have to know how and where to find those conversion factors. So not only do you need to know the process, you have to be able to know the knowledge of where to find conversion factors, which makes it more difficult. Okay? And those unit systems in the next part of our class aren't things that you can use with a simple algorithm. Okay? So, there is a video that goes over the basics of this with some simple examples. Okay? I expect you to go through and watch that. It's only half an hour. If you've watched that, this next part shouldn't be too bad. What is the speed in meters per second of our bicycle? Step 1. $1,000 meters. I know where you're going with that. That's not step 1. Ultimately, that would be step 3. What is step 1?
Just meters.
No. Step 1 is identify what you're trying to get to. What are you trying to get to? Meters per second. What does per mean?
Every.
What's that?
Every second.
Every works. The more important one, or the more relevant one, I think here is going to be divide. Okay? So meters per second. What are we given? We're given kilometers per hour. Okay, so I'm going to write hours, kilometers. Does that make sense? No, why not?
You're not going 105 hours per kilometer.
Okay, I'll fix that. I'm going 105 kilometers in 1 hour. So I invalidate your argument. Your argument was solid, but sorry. Why is that still wrong?
Meters is on top on the right side.
Better. What is meters a measure of? Distance. Where do I want my distance unit to be? On top. When I wrote this out, what did I put as where did I put my distance unit? On the bottom. Does it make sense to do that? No, because these are supposed to be equalities. They need to balance out. Where I place those units doesn't make sense with where I want my answer.
Something to do with those.
Start with 1,000. I'm not saying you're wrong. But I'm definitely not saying you're right. Kilometers over hours. I have 105 kilometers in 1 hour. Are those two things the same? Is kilometers the same thing as meters? No. Is hours the same thing as seconds? How do we know that? They're different letters. Okay? The language is literally different. That's how we know they're different. Okay? So in the course of everything in the middle there, I have to make kilometers become meters. I have to make hours become seconds. What do you want to do?
You need to add another dash mark in the middle.
Okay? I need to do something in the middle here. In that something in the middle, what do I want to do?
You want to have a chain on the bottom.
Okay? So Nick here is saying, hey, I don't want kilometers in my answer, so I want that kilometer unit to be in the denominator so that it cancels out. What unit do I want to show up in my numerator? Meters. So I'm going to place meters up here.
1,000.
Am I responsible for knowing that conversion factor? Yes. K means
Kilo.
touche, kilo, and yes, 1,000. I'd prefer the power of 10. 10 to the third, it's okay. Okay, and as long as you're consistent on it's okay. Where does our power of 10 always go? With the core unit. Which is the core unit? Meters or kilometers? Meters. 10 to the third. What goes underneath? 1. That's how it works. What happens? Kilometers cancel, and I would now have meters. Hell yeah, I'm done then. No? What do you mean? Oh, I'm still in hours. So what do I have to do?
Another dash.
I have to do another dash. In that other dash, what needs to happen?
Seconds on the bottom.
I need what?
You need meters on bottom.
Do I want meters on bottom?
Hours on top. Seconds.
Okay. So focus on what we're now looking at. We're now looking at moving hours into seconds. Does hours show up in my answer? No, which means where does hours need to show up in this conversion? On top. Okay. What do I want to show up on the bottom? Seconds. Okay. For those of you that know this, well, actually, let's try it this way. How many of you know the conversion between hours and seconds? Okay. At least half the class said they didn't really know it. Okay. That's fine. Okay. It is something you could calculate. I would argue you shouldn't be doing that, but that's okay. So we don't know that conversion. Okay. So I can't go hours to seconds. Oh, we could go hours to minutes. Okay. This does help because this gets rid of the hours. I don't want hours in my answer, so this is progressively moving forward. Okay. It's getting rid of the hour unit, but that assumes I know the conversion factor between hours and minutes. What is that conversion factor? 60 minutes is in 1 hour. Okay. Now what happens? Minutes needs to cancel, so I place it in the numerator. What do I want in the denominator? Seconds. Why? It's where it is in my answer. Do I know that conversion factor? What is that conversion factor? 60 seconds is 1 minute. The minutes cancel. What am I now left with? Meters per second. Now, that my units have told me where everything goes. Now it's a question of me just entering it into the calculator correctly. So to enter it into the calculator correctly, this is my recommendation. I would take 105 times 10 to the third, okay, divided by 60 times 60. Where did all my units go? I did the unit work already. I don't care about it anymore because I know the units are lined up. Okay, 105 times 10 to the third. My calculator is going to tell me it's 105, 1, 2, 3. 60 times 60, the calculator is going to tell me it's 3,600. Whoa. Let's try that again. 3,600. Now I'll enter into the calculator 105,000 divided by 3,600, and now I'll get my answer, whatever that comes out to be. Does that make sense? Okay. The reason being is that if you just go into the calculator and say 105 times 10 to the third divided by 60 times 60, what happened?
Well, if you use parentheses.
This second 60 is no longer in the denominator, it's in the numerator, and you get the wrong answer. Okay? So if you want to run it as one line, that's fine. You just have to make sure that you include and let the calculator know that both of those 60s are in the denominator. You'd have to include parentheses. Okay? Or you go through and do it my way, where you just multiply the top, multiply the bottom, get a number, do the division. Kind of make sense? Part of this class is dealing with the calculator. This kind of question, I would argue, is a show your work. So part of it would be the actual answer. The primary part of this question would have been in the show your work. Okay, what do you need to show for your work? Everything that's written up there. Well, except for this stuff. You don't need that. Or this. Okay? Make sense? Okay. Get the basics of how to set up the solves. Is that a yes or a no? Yes. Okay. You should be able to go through and do all of these examples. Okay. These are all fair questions. You're just doing different conversions all the way through. Okay, in differing amounts. One of the things that students tend to kind of go, well, this is a bit silly on, comes back to, again, well, I know how to do those conversions. It's not a big deal for me. I can just multiply, divide. I know how to do all that. Okay? You've created an algorithm because you understand those units. The instant you don't know those units, the next sequence of material, you don't have a process to be able to solve. Okay? Which means every time you place a fraction, you could be placing that fraction in the wrong place. So instead of it being 105 kilometers over 1 hour, you place 1 hour over 105 kilometers. There's only two ways you could do that. So that's a 50% chance that you get that calculation correct. Everybody understand that? What about the next one? Well, if you don't have a process, your 1001 could be placed in different places, which means there's a 50% chance you get that one placed right. And a 50% for the next one. And a 50% for the next one. So just blind guessing your way through this, that one dropped to 5% all of a sudden. You might say, well, for an individual calculation, that's only 50. God, it's still 5%. Okay. You might say, well, that's not that bad. 50% is failing. Don't do that. You need to know why you're placing the numbers where they are. It's the units that dictate it for you. Add to that if there's multiple conversions, 50% of 50% is 25%. Just having two things that you're multiplying by each other, the odds of you getting the question right by luck, 25%. What is 50% of 25? 12.5. 50% of 12.5. 6.25%. The odds of you getting this question correctly by blind luck is 6.5%. That is not a passing grade. Okay? And you may get one right. That's awesome. One out of those right, you're now still at 12.5%. That's still failing. You get 3 of these 4 processes right. You're still failing. Okay? So you have to trust the process because the process sets you up. That process is all about the units. Okay? I highly encourage you to go back through and look at this video and look at how we solve this. Right? And watch what I wrote when I wrote it. The very first thing was meters per second. What was the next thing I wrote? No, I did not write 105. What did I write? Kilometers per hour. Then what did I write? The 105 and 1. Yeah. But I addressed the units first. When we did the conversion here, what did I write? Kilometers, meters. Then the numbers. The next one was hours and seconds. Oh, I didn't know that. So we deleted seconds and made it minutes because I knew minutes. Then I wrote the numbers. The numbers are utterly meaningless and useless without the units. Write the units down. Okay? And you got this. Trust the process. You will absolutely get it right every single time. It's phenomenal. Yes?
If we do 1,000 meters instead of 10 to the third, is that okay, or does it need to be 1,000?
You can do 1,000 meters instead of 10 to the third. The only reason why I stick to 10 to the third is that what I have you do is memorize kilo is 10 to the third, centi is 10 to the negative second, milli is 10 to the negative third. So if we keep it as a power of 10, it's consistent. Okay? If we start shuffling it and saying, well, that's 1,000, then centi is 0.01 and milli is 0.00, and I don't want to deal with that. So if we stick it with the power of 10, it's okay. Okay? I know why you want to do 1,000. How many of you like exponents? Oh yeah, nobody. Okay? Believe it or not, way back when, nobody liked exponents too. Which is why when we talk to somebody who's done a bunch of science, do they memorize that 1 centimeter is 10 to the minus 2 meters? No, what do they memorize? They memorize 100 centimeters is 1 meter. Why? They didn't like the power of 10, and they really didn't like the negative power of 10. So they converted the number around to make it easier for them to manipulate. The argument that I would make is the reason we did that, very simply, we didn't have calculator for this exam. A calculator, and no phone calculator, sorry. You will all have a calculator, and your calculator will have powers of 10 on it. If you don't have a calculator, you need to go buy one. You can get a cheap one that does all the powers of 10. We aren't done. Right? So you've got your compound units to go through and manipulate. Percents, we talked about percents, so we're not going to do it again. Percents are the same thing. They're another conversion factor. You're relating one sample to another. That's it. Okay? So it's the same concept as our conversions. Volumes. So we looked at converting between masses and distances and all that, and those are kind of straightforward. Volumes get a little bit more interesting. Okay, volume is how we measure a liquid. Liquids we can't measure as a mass quite as easily, so we built containers to hold the liquids. Then we could go, well, I could measure the volume of the liquid. If I put markings on my container, I now have a way to standardize how much liquid I measured out. Okay? So the easiest container to measure for a volume would be, squares don't work for three-dimensional space, cubes. And to measure the volume of a cube, it is length times width times height. So if I look at the volume of this cube, it would be 10 centimeters cube. Oops, let's try that again. 10 centimeters times 10 centimeters times 10 centimeters, which is 10 cubed centimeters cubed, also known as 1,000 centimeters cubed. I could use that distance unit to measure my volume. I decide not to. Why? Is volume the same thing as distance? No. So I want to emphasize the fact that I'm looking at a volume, not a distance. So what do? I invent a new unit. What new unit do I invent? Liters. 1 liter is 1,000 centimeters cubed. What does cubed begin with? C. Centimeter begins with C. Anybody heard the shows, doctor shows, give me 20 cc's, whatever, stat. cc is a cubic centimeter. Okay, it's a measure of volume. All they're talking about is get me a volume of that drug. Okay? Turns out that centimeters cubed is the same thing as milliliters. 1 liter is 1,000 milliliters. Okay, so centimeters cubed and milliliters are the same thing. Okay? You could go through and do that conversion. I don't want to deal with that right now, but I do want to hit you up with this one. Okay, length volume conversions become challenging to deal with, which could be the other reason why we invented a whole new system so that we don't have to worry about this confusion. Okay, what am I being asked to solve for?
What is the displacement of centimeter cubic inches?
So I want what unit?
Inches cubed,
Inches cubed. What am I given?
centimeters cubed.
Okay, centimeters cubed. How many? 498. What do I know needs to happen in the middle? I got to get rid of centimeters, and what do I want?
Inches.
Inches. Do I know a conversion factor between inches and centimeters?
It's probably assumptions.
Okay. 1 inch is 2.54 centimeters. I don't expect you to memorize it, but it is a common one. Okay. Would that work? No, right? That's centimeters cubed. That's just centimeters. So I just have to cube this. And now I'm done. What do I divide by? 498 divided by?
2.54.
No. I divide by roughly 16. Okay.
Cube it.
Because that cube applies to the number in front, not just the unit. Okay? The way that we can really break this down to call attention to it, 1 inch is 2.54 centimeters. If I just did one of those, that cubed becomes squared. If I do a second one, if I do a third, I get rid of the whole centimeter. You have to be very careful when doing volume conversions with distances. Okay? When you cube, you're cubing the number in front as well as the unit. You can either always know that that's what's happening, you're distributing it, or you show it all the way through. Okay? Volume conversion factors are notoriously a trap to trick students into this system where you then ultimately get the question wrong. Okay? With that, we're done.